So our next lesson in Algebra 2 is going to cover a real basic level of inverse functions, and we're going to talk about their usage and properties of inverse functions in comparison to their original function. And these are the big 5 properties of inverses that we need to know. So in order to find an inverse, the basic idea is that the x's and y's have switched. So the input and the output have switched places. And because of that, it makes sense for me to say that the domain and range have switched. So another property of inverse functions is when you graph them on the same coordinate plane with their original, they're going to be reflections over the line y equals x, the identity graph. We'll see why in a second. I mean, it makes a lot of visual sense once you look at the graph. The inverse is a function if the original passes what we call the horizontal line test. Now that should seem a little familiar. It's very close to the vertical line test, but remember we're talking inverses. So instead of passing a vertical line test, the original would have to pass a horizontal line test, which means that his inverse is a function. We'll talk more about that in the lesson. And then the last one about the composition, basically they're saying that inverse functions undo the original function. That's the whole point of the inverse function, is to undo the work that the original function has done to x. So if you were to do what's called composition, f of g of x and g of f of x, you would result back with just an x. They would undo everything. So when one function added a 3, the other function would subtract a 3. When one function multiplies by 5, the other function would divide by 5. Everything in inverse functions makes lots of sense once you kind of look at it. So the first property that they illustrated about just switching the x and y, we're going to see here on this first example. We have a relation that is a set of ordered pairs that are just given in like a table format. And it says, well, what's the inverse? Well, you literally just switch the x and y's around. So I'm going to take all of these y's, I'm going to write them in that same order, 4, 2, 0, negative 2, negative 4. And then we do have to make sure that the x's and y's match up the same way they used to. And now the x's are y's and y's are x's though. So the y's become negative 2, negative 1, 0, 1, and 2. That was it. So this next function it's a continuous function, it's a line. So it's not as simple as just giving a bunch of ordered pairs and switching them, because this function continues forever. So instead, algebraically, we're going to switch the x and y around. So x equals 2, and then I'm going to do the y in like red, because if I think about what I usually do for providing functions to my teacher, usually they're in y equals format, and that's what we're going to have to do here. So basically we're going to isolate the y. So think about your isolating skills. Bringing everything away from the y, my first step would be to add this 4 over. Good thing we did all this work last semester, huh? You guys are real good at isolating. So this is x plus 4 equals 2y. And then I still want to isolate this y. So my last step in this problem would be to divide by 2. Now you can just do one big fraction bar divide by 2 like this. You can also divide by 2 separately, which is typically what we see. Now I'm going to take the liberty of switching this around because I don't like the order. And the other thing I'm going to do is, instead of calling it y, because how am I going to know if he's the inverse or not if I just call them both y? I'm going to use this notation, y to the negative first power. That represents inverse notation. So the inverse for y is x over 2, which I'm going to write as 1/2 x, and then 4 over 2 is plus 2. There we go. So now I can see the original function is 2x minus 4. His inverse is 1/2 x plus 2. They look very different. If we graph them together, you'd see some relationships. All right, number 3, same idea. We have a continual function, so I'm not going to be able to give just ordered pairs. I'm going to have to turn the function inside out. So x equals negative 2/3 and then y plus 6. And then same thing as the last question, you're going to have to isolate the y for me. So let's subtract the 6. And we end up with x minus 6 equals negative 2/3 y. And then the easiest way to get rid of a fraction coefficient is to multiply by his reciprocal. So the reciprocal of negative 2/3 is negative 3/2. And if I were to distribute or multiply that to everything over here on the left side, I'm going to end up with, and again I'm going to use that inverse notation, y inverse, because these are going to cancel, is, let's distribute that, negative 3/2 x, and then negative 3/2 times negative 6 is a positive 9. If you don't want to do that in your brain, just use your calculator. All right. So this next function, it's like a parabola, and when we move on to college algebra and math 4 and pre-calculus, we'll talk more about issues that we have with the domain of this function and his inverse. But for algebra 2, I'm not going to worry about that. Let's just do the algebraic manipulation here. So we're going to switch the x and y around. And then I'm going to do that y in red, so we know to isolate it. Alright, so first step in isolating here would be to subtract the 8. So we end up with x minus 8 equals 2, and then y squared. Okay, I'm going to have 2 more steps actually to isolate the y. First I'm going to divide by 2. And because of the nature of this question, I don't mind if you just leave it as a big old divide by 2 for everybody. So x minus 8, all of that over 2 equals y squared. And then my last algebraic step to isolate the y would be to square root both sides. And we end up with inverse function for y being, this is where we're going to run into a little bit of trouble with like the upper level teachers. For now, for algebra 2, let's put plus or minus square root of x minus 8 over 2. Turns out what we just came up with is not actually a function if we write it that way. We'll talk more about why that is later when we talk about the horizontal line test. So when you move on to your 4th year math class, this is not actually what you would have done in your 4th year math class. They're going to restrict the domain and give you a partial function, partial piece of that function, and then you'll have an inverse function. But for algebra 2, we're not going to worry about all that. We just want to talk about how to switch the x and y and solve for y. Alright, so of course I can't read what's under here because that's in my way. Alright, what? Alright, whatever. You ever have one of those days? I think I'm having one. Alright, so switching the x and y around, this is just a line, so nothing weird happening here. X equals 2/5 y minus 4/5. So first thing I notice is there's a lot of fractions, and I really don't want to work with fractions anymore, so I'm going to take the liberty of getting rid of those fractions. What if I just multiply everything by a 5? I don't have to do this step first, but, you know, I like it because I really don't want to work with fractions if I don't have to. So this becomes a 2y and then a minus 4, excuse me. Alright, now I'm going to isolate the y. We're going to add 4. So we have 5x plus 4 equals 2y. And then one last step, we're going to divide everything by a 2. And because this is a line, I'm going to go ahead and divide the terms separately by a 2. So I'm left with the inverse for y as being 5/2 x plus, instead of 4 over 2, let's call that 2. There we go. Please make sure you use that notation of y to the negative first power to mean the inverse of the y. That way we can signify who's the original and who's the inverse. Alright, speaking of originals and inverses, for number 6, this line right here that we graphed, this is the original function. So they didn't even give you the inverse function, and because of our lack of experience with inverses, you probably have no idea what an inverse function even looks like, and that's okay. But the original function tells you a lot, and I keep calling this a function, but I probably shouldn't, because the original is actually not a function. Because notice this guy would fail the vertical line test. So the original isn't even a function. However, he does pass the horizontal line test. Those are supposed to be horizontal lines. So the original passes the horizontal line test. What that means is that there is an inverse function. The inverse is a function. Because the idea is if the original passes the horizontal line test, then the inverse would have passed the vertical line test. And since I don't know what the inverse looks like, I have to kind of trust this horizontal line test. Alright, so again here on number 7, this is the original. And he does pass the vertical line test. So the original is a function. However, look at that. The original fails the horizontal line test. What that means is my inverse is not a function. Because the original is going to fail the horizontal line test, meaning the inverse would fail the vertical line test. Alright, so we had one where the original was not a function, the inverse was, and then we had one where the original was a function, but the inverse wasn't. And then let's look at this next one. So we have our original here, and he's going to pass the vertical line test. So he is a function. And then I noticed he'd also pass the horizontal line test. And what that tells me is that the inverse is a function. Sorry for the sloppy handwriting. So, if this function, this original is a function and the inverse is also a function, so it passes the horizontal and vertical line test, this is a special function. This is called a one-to-one function. We're not going to talk about that too much in Algebra 2, but when you move on to pre-calc and college algebra, Math 4, you'll see a significant amount of talk regarding one-to-one functions. Alright, this is just more practice of doing the same stuff, guys. What I would like to do is, alright, I'm going to pull up a coordinate plane, maybe. I want to do number 9. We're going to skip number 10 for space, so if you want to steal space for number 10, that's fine. I'm going to draw the inverse and the original on a coordinate plane, so you guys can see what that looks like. Through the art of technology, here we go. Alright, so the original function is f of x equals 2x minus 4. If you don't like the f of x, change it to y. But that's a line that starts at negative 4 and then has a slope of 2. Now I'm asked to find the inverse function, which means I have to do my algebraic switching, where I switch the x and y around, just like we did on the last part of the notes. I'm going to isolate. So we end up with x plus 4 equals 2y. I'm still trying to isolate for y, so I have one more step. I'm going to divide everything by a 2. And I'm going to divide them separately because I do have to graph this line in a minute. And then instead of calling it y inverse, remember the original problem? We set this up as f of x is the name of the function. So his inverse, we're going to use that same negative 1 power notation to indicate the inverse function of f, is 1/2 x plus 2 if I reduce those fractions. So what I'm going to do next is I'm going to graph this line in red over here on the same coordinate plane. So it starts at 2, and then the slope is 1/2. So up 1 over 2, up 1 over 2. That was a really bad job. I could go down 1, left 2, down 1, left 2, and then, you know, like, oh boy, that was supposed to connect. You should see the graphs I've done today, guys. It's been really bad. Okay, this is what I'm trying to illustrate to you. The inverse and the original, remember those properties that says the x's and y's switched? So like this ordered pair here is 4, 4, and both of those functions go through the point 4, 4, because if you switch 4, 4, it's still 4, 4. But like this ordered pair right here is 2, 0, and then this ordered pair here is 0, 2. So notice they have like very similar points, they're just reflected and switched around. This is the ordered pair 3, 2, and this is the ordered pair 2, 3. So I could have kind of come up with the graph of the inverse if I just took some ordered pairs in the original and switched them around, but this is what I want to illustrate to you. One of the properties at the beginning of our lesson said that they were reflections of each other over the line y equals x. Well, y equals x is the identity line. It goes through the origin, has a slope of 1. This green line I'm trying to draw here. And they're symmetrical about that line. If I were to fold the paper right along that green line, they would be mirror images of each other. So that's what it looks like when I say an inverse and its original function are reflections across the line y equals x. So I think that's a nice job of illustrating, frankly, many of those properties that we saw on that chart. We're not going to talk about composition of functions as to why inverses undo each other. We just don't know enough about composition yet, but when you move on to your next math class, you'll see more of this. Alright, I'm going to look ahead and see if there's oh, you know what? I would like to look at number 11. This is a nonlinear function. But same idea, f of x is fancy talk for y. So when I go to find the inverse, I switch out the x and y. And then I still want to solve for y. Now this is a little unusual because like it's not as easy to isolate the y because it's kind of trapped inside of a fraction. So my trick for untrapping fractions is just to cross multiply them. And that turns them into regular old like linear equation. Well, they're not linear equations, but they're written in a line. So x times y is equal to 4 times 1, which is 4, And then if I think about what would I do next to solve for y, I would divide by x. So this is a little unusual. And again, I'm not going to call it y inverse because the original function was f of x. I'm going to call this inverse of function f. Alright, 4 over x. Do you notice anything kind of weird? The original and the inverse are the exact same function. We'll learn more about what this graph looks like when you graph it next year in math, but it's a rational function and it has symmetry along the line y equals x. So like when you map itself along that line, it just lands on itself, basically. He is his own inverse. It's a really strange function. Alright. I think we'll stop the lesson there. That's a good intro into inverse functions. We're not going to do a ton of work with inverse functions in Algebra 2, but it's going to come up a lot in your next math class.